Greetings, everyone. My name is John Clayton of Hazen and Sawyer. Today I'll be speaking on behalf of Zeng of Georgia EPD. I am a project manager on EPD's contractor to develop a new approach to statewide basin modeling in Georgia in support of both regional water planning and evaluation of proposed new water use permits and permit changes. Models built under this new approach have been coined Basin Environmental Assessment Models, or BEAMS. The EPD and Hazen team have been working on this new approach since mid-2019, focusing on new methods for defining basin nodes and resolution, inflows, and analysis of results using a new modeling platform. Over the first year, we developed our new methods using the Oconee, Ocmulgee, and Altamaha, or OOA, basin as a pilot study. Currently, the OOA beam, as I show today, is undergoing final refinements. The team is currently developing beams for the Savannah Ogeechee, or SO, and the Ocmulgee, Sewanee, Satilla, St. Mary's, or OSSS basins. We've also recently kicked off efforts for the remaining basins, including the ACT, ACF, and Tennessee. Today, I'll focus on introducing the process of developing the OOA beam model. I will discuss general model configuration and features, and I will give an overview of how unimpaired inflow time series, the primary input for this type of model, are developed for this framework. I will briefly touch on how the beams and the UIFs are verified. I can go into a little more depth during Q&A on that, but any results are preliminary given the final refinements that are currently underway. I will then illustrate the capabilities of the new approach through a hypothetical scenario using hypothetical performance metrics that differ from those used in past regional planning and permitting evaluations. The biggest difference in the prior basin modeling approach and a new approach is spatial resolution. On the left, you see the schematic for the OOA ResSim model used in prior regional planning efforts. In this model, consumptive use is simulated in aggregate at 11 planning nodes. And this consumptive use includes the total of industrial, municipal, and agricultural withdrawals, municipal and industrial returns, thermal losses from power generation, and operations on all reservoirs except for the largest ones, Jackson, Oconee, and Sinclair. Reservoir operations are directly simulated for these reservoirs, these three largest reservoirs. Flows between planning nodes and reservoirs are simulated between the 11 planning nodes plus 5 additional model nodes, and flow simulations include time of travel. On the right, you see the schematic for the OOA beam model. The OOA beam is constructed using Hazen and Sawyer's OASIS modeling platform. In this model, consumptive use is modeled individually for each water using facility in the basin. Here we go. This includes withdrawals and returns for each municipal, industrial, and thermal permit in the basin. Beyond the 3 major reservoirs, each individual water supply reservoir is modeled explicitly, using the best available information on geometry and operations. Agricultural withdrawals, while not modeled on an individual irrigator basis, are aggregated at approximately 12 geographies, which is a very fine scale. This further zoom more clearly shows the structure of a beam in general and the range of features included. Like ResSim, the beam consists structurally of nodes connected by arcs. The backbone of the model consists of junction nodes in yellow, which are points of interest along the stream network. Arcs connecting junction nodes form the stream network itself. In beam, nodes represent individual return and withdrawal facilities, such as the dark blue and the light brown shapes there, aggregate agricultural withdrawals in the dark brown, reservoirs in the red triangles, and USGS gauges, the pale blue round things. Each of these is connected to a junction node. In fact, junction nodes are largely defined by the need to connect one or more facilities to the network. There are also nodes for unimpaired inflows at each junction, and these are the small green symbols. These represent the incremental unmeasured inflows to the system upstream of each junction. Unimpaired inflows to the model are assumed to occur at these points. In B, time of travel is simulated for selected reaches using routing reservoirs, which are these pink trapezoids. Okay, these replicate the delay of flow by temporarily impounding water in imaginary reservoirs and then releasing that storage downstream at attenuated and lagged rates. Because the resolution in Bean is so much higher than in the prior model, many of these individual reaches are much shorter, meaning that time of travel is only significant and in need of modeling for some of the reaches. The output of the beam is what you might expect, given a set of inflow time series and the withdrawal and return demands, permit rules, and operation rules for reservoirs. The beam simulates the daily stream flows, withdrawals, and returns as limited by availability, or the permit and lake storage elevation. These simulations are available from every node in ARC in the schematic. One important difference between the prior method approach and the new approach is how withdrawals and in-stream flow protections are treated. In the prior model, withdrawals were given precedence. A demand was modeled to be satisfied even if the resulting stream flow would fall below protection thresholds. This was necessary because water uses were modeled in aggregate at planning nodes, making it impossible to compare individual demands and flow limits. Resulting flows were then compared to limits defined at planning nodes, identifying as gaps those times when flows fell below thresholds. In Beam, on the other hand, the in-stream flow is given precedence. Withdrawal is simulated only to the extent that there is sufficient water above the threshold at the withdrawal location. Resulting withdrawals are then compared to demands, identifying as shortages those periods where demands cannot be met while protecting flow thresholds. These periods are then flagged during planning and permitting exercises as areas of potential concern. There are a wide variety of input data sources used to develop a beam, including withdrawal and return data and permits, which come from EPD, operational and physical characteristics for the largest lakes from Georgia Power, rainfall and evaporation data that come from EPD and public sources, information on smaller reservoirs such as surface area evaluation curves or SAE curves, and release rules from EPD, and that comes from EPD in contact with individual reservoir owners. And then the main input are the unimpaired inflows, which are produced by the team using many of these same sources. Unimpaired inflows are perhaps the most critical input to any basin water quantity model. These are defined as the historical inflows that would have entered the stream through rainfall and runoff and other natural sources in absence of any human modifications or influences. In general, for these types of models, historical inflows or observed ones are first determined using USGS gauge data. Those data contain the impacts of any withdrawals, returns, and what have you. Then any locally observed or estimated historical withdrawals, returns, or other modifications to those gains, these are labeled in red, are removed from those gains. And what remains is the unimpaired inflow that would have occurred absent any human presence. With these inflows available as inputs, alternative human modifications, such as changes in demands, returns, or operations, can then be simulated by a basin model, and resulting impacts under historical hydrology can be assessed. This seems very detailed, and I could tell you that the development of UIFs for a beam is even more detailed than this. In the OOA beam, we start out by producing monthly UIFs between about 40 pairs of USGS gauges throughout the basin. We then disaggregate those to the individual inflow nodes that we defined before using drainage areas, and we disaggregate from a monthly to a daily time step using monthly to daily flow patterns taken from rainfall runoff models or from nearby gauges. I invite much more Q&A on this topic. It's really too much to go through here. So, one major benefit to the new beam approach is that it provides a much richer set of ways to evaluate how water use influences basin characteristics. Flow and elevation results can be harvested from nodes representing individual use locations and their environs, allowing water supply reliability to be assessed for individual users or collections of users. Changes to reliability throughout the basin can then be assessed under localized hypothetical or proposed changes in permits or operations. Furthermore, to the extent that localized flow rates can be translated into indicators of ecological, recreational, or other conditions, the implications of permit changes on these other uses can also be assessed. Anytime, and we do that through the definition of performance metrics, anytime we define a plot, a table, or a summary number that indicates the suitability of hydrology for some defined use, we call that a performance metric. Given the resolution of the beam approach, the list of potential PMs or performance metrics is vast. Here are some example PMs that might be stipulated for the OOA beam, just off the top of our heads. When looking at water supply, one can look at the daily volume of desired withdrawal that cannot be taken from a river because of low flows or from a reservoir because of low elevations. Ecologically, if one had a relationship between stream flow and an area of habitat suitable for a specific species of fish, one could treat the simulated habitat area as a PM. For recreation, if a minimum river level required for boating were converted to a flow value, number of boatable days per year could be used as a PM. These are just a few examples, but it shows the means by which various stakeholder concerns can be addressed by the beam approach. One needs a relationship that turns flow or elevation coming from the model into a proxy for whatever concern you have. One good source of information that we were able to use in an example here was the flow regime evaluation methods of the Ocmulgee River in 2019. It serves as a great illustration of how this can be done. This report establishes stream elevation and wetted perimeter criteria for several recreational and aquatic habitat metrics, including paddling and boating, fish, and floodplain wetlands. Using known relationships between flows, elevations, and perimeters in the middle Ocmulgee, along with these recreational and habitat criteria, we developed a hypothetical planning scenario. Let's say that there's a new industrial demand of 50 MGD with no return that's going into the Ocmulgee Basin north of Lake Juliet. And we want to know if there's any potential downstream impacts to downstream water supply, recreation, and fish habitat. Will pumping to Lake Juliet be impacted by the new demand? We evaluated that, given that it's being pumped from the Ocmulgee River, and recognizing that the permit says there are in-stream flow protection limits for the pumping that vary with the elevation in the lake. When the lake is below 428 feet, the minimum flow requirement in the river is 410 CFS, and when it's above 428 feet, it's 931 CFS. We did this evaluation over a test period of 2000 to 2018. Looking at the time series of elevations, we definitely see an impact of the new demand on flow at the pumping point. I'm sorry, not elevations, flow. Looking at the time series impact of flow, we definitely see an impact on the new demand on flow at the pumping point, but does this result change in the frequency with which pumping can occur? The plot I'm showing here is a performance metric that compares the number of days that pumping is restricted each year relative to the 1931 CFS threshold with and without the new demand. In other words, it shows the number of days pumping is not allowed, given that Lake Juliet is above 428 feet when you're pumping. Indeed, there is an impact. It's larger in some years and smaller than others. But on average, the impact is an increase in the percent of time pumping cannot occur. And it goes from 41% of all days to 44.3% all days, or in a given year, roughly 12 additional days where pumping is restricted. Under the condition of a lower reservoir, so the 410 threshold, pumping is not as restricted as much, and that's by design of the permit. There are some years where the flows never get below 410 CFS, even with the new demand, such as 2003 and 2005. However, where there is an impact, it is larger than before in terms of the number of days where pumping cannot occur, as indicated by the larger differences in the bars. On average, the impact is a reduction in the number of pumping days per year from 318 to 292, or 26 days. So look at some other places that might be impacted. How about pumping to downstream water supply reservoir, like Macon Water Authority's Town Creek? Take a look at their permit. They have no in-stream flow requirement so long as the pumping is below 35 MGD. The result of this simulation is that there is no impact to storage at this reservoir from the new demand, simply because there's no lower flow limit that we're dealing with. Because there's no flow limit and there's physically always enough water to support withdrawal, this reservoir is simulated as being kept full, and demands from withdrawals off the reservoir are always able to be met, even with the new upstream demand. How about kayaking? If we adopt the USGS stage flow rating curve for the Macon gauge, we can convert the minimum boating depths of 6 feet to a minimum flow of about 930 CFS, as shown here. Then we can run beam and determine the number of days each year with and without the new demand that gauge flow is under 930 CFS. This shows that there's an impact in most years, often on the order of reduction of about 10 days per year. And how about fish habitat? This can get a little more complex because the relationship between the amount of habitat and flow is nonlinear and can be a lot more complicated, as shown here. Here's two examples where the amount of area-weighted habitat suitability on the y-axis is related nonlinearly to flow on the x-axis, with peak habitat availability at an ideal range of flow for different species. Higher, implying that higher weighted suitable habitat means more habitat, which here we assume is a good thing. The black curve shows habitat versus flow for shallow, fast swimmers such as spot-tail shiner and bluehead chub, while the blue shows habitat versus flow for deep, fast swimmers such as largemouth bass. When we apply those curves to simulated flows with and without the new upstream demand, we get time series of area-weighted habitat suitability, which then we can plot as cumulative density functions. In the example of Shiner and Hub, there's about a 25% of the time where habitat is at a minimum, regardless of the presence of new demand. The other 75% of the time, the presence of the new demand actually increases the amount of habitat for these species, as reflected by the red line above the blue line, indicating that reduced flow from the upstream demand actually creates a better flow regime for these species. How about bass, largemouth bass? Looking at the same types of plots, there again, is a 25% of the time where there's no impact on habitat from the new demand because that habitat's at a minimum. But then at other times, the impact of the new demand is mixed. When the habitat is lowest, there is a slight improvement in habitat amount. But then when you get to intermediate levels, evidently due to the shape of that curve, the relationship curve, the new demand reduces habitat. And then when we get to the highest levels, there's again not much impact. So it's pretty cool what you could get from applying some of those relationships before to really detailed simulations of flow and elevation at different spots in the basin. I want to stress that these are just demonstrations showing conceptually how it's done and how it opens up the possibility to incorporate stakeholder concerns in permitting and regional planning. Basically a larger variety of impacts can be defined in more location and user-specific terms. This capability arises from the fact that the BEAM approach adopts a facility-specific resolution. As I said at the beginning, we're completing refinements on the OOA right now. We're in the middle of development for the OSSS and the SO, and we are just beginning development for the remaining basins. It's envisioned that by nature, these will be living models, that they are adapted as new users arise and join in, and as operational policies and demands change. And it's really been a team effort. It's taken a team effort to develop this. EPD included, they are very engaged in technical collaboration from strategizing to implementation. And I can tell you, we're all really enthusiastic about this new tool and what it can do. And we hope that you see value in some of the new possibilities. Thank you very much, and I look forward to your questions.